All right. Well, good morning, everybody. We have some folks still coming in. So just one item of business before we get started. So the structure we had yesterday is what we're going to repeat today and tomorrow, with everybody working on the same module in their breakout groups in the morning. We'll come back around 11:30 or so for a recap conversation, give some feedback. You'll have from 12 Eastern till 2 p.m. Eastern for lunch, brunch, taking care of kids, taking care of household things, taking care of work things, whatever you need that 2 hours for. And then we come back in the afternoon for that breakout sessions with choice time, where we let you pursue whatever options you want. Some of you jumped between a couple of breakout rooms yesterday, so hopefully you enjoyed that freedom. The one exception to this is Friday. We are only scheduled to go until the end of the morning session, so we won't have an afternoon breakout session, but we have received an invitation to go crash Adam Lemie's QuarkNet workshop that afternoon. So if you don't have any plans Friday afternoon and you would like to go meet some other physics education folks, we will have that link for you on Friday. I invited Adam as a facilitator, and he said, "Oh, I'm actually leading a workshop, so maybe next summer we can trade workshop participants, and they can come over here, and everybody can go over there." Terry and Mark, are there any other announcements or logistics we need to share before we get underway today? I'm seeing shaking heads. So why don't we take a couple minutes for a recap from yesterday? So feel free to unmute your microphone or type up a message in chat. What stood out to you from yesterday, and what would you like to learn more about?
I think I would need some practice with the language itself. It's like putting a puzzle together.
Yeah.
And I feel like I don't have all the pieces yet.
Okay, so let's press that analogy. What is the equivalent in programming of finding the corner pieces first?
Then when you type in NP, I guess.
Yeah, some of you learned that if you just start typing something, DeepNote is kind enough to give you some autofill suggestions. And a lot of times when you get an error message, it will even give you a URL to Stack Overflow to search for that error message. Google Colab has the same type of structure there. So it's okay to step into the unknown, right? It's okay to start with those corner pieces and say, well, I know I need to do this, and then kind of find your way forward. Summer says in chat, the scaffolding of the Jupyter notebooks was awesome to help guide students along with computational thinking, right? So we're kind of pursuing several tracks at once with these, right? Obviously, we want to teach the students physics, right? We are here because we're physics educators. We want them to learn the language, right? The syntax, and we want them to start thinking in terms of computational thinking, to approach those physics problems in an iterative, algorithmic problem-solving fashion that's a little bit different than what they're doing, when they solve something by hand. Tom says, understanding lists, arrays, and dictionaries. Tom, where did you meet dictionaries yesterday? I don't remember seeing that in Falling Through the Earth.
Yeah, it might have been in the breakout session for what did I do yesterday afternoon? I'm blanking out on it.
Visualizing electrostatics.
Yeah, I know they were in the electrostatics one.
Yeah.
Yeah, so I use lists in that notebook because you want to describe a charged particle. Well, charged particle, I need 3 properties. I need its x coordinate, its y coordinate, assuming we're in a plane, and I need its charge value. And that's not a nice, clean vector. So we made that a dictionary so that you could say this charge x, this charge y, this charge q value, and then you can just pull off that information there. Cool. Janice, I see you've got a hand up. Go ahead.
Yeah, so what stood out, just like how complete the package is in terms of developing a lesson plan. Like you have the instruction, you have the material, you have the assessment all built into one neat little package. which is awesome. That kind of just blew me away. But I can't use it unless I can learn how to program the language.
Yeah.
Because I need to know it well enough to teach kids how to use it. So right now I see the awesomeness of it, but right now it's useless to me because I don't have enough facility with the language.
Yeah, I mean, think about if your students, you know, obviously they're going to need some initial training too, but think about once they get past that initial training, the lab reports they could write.
Yeah, that's the, and all in this one neat little package. Like,
yeah, exactly. Walter, go ahead.
To put a little bit more fine-grained detail on that comment, one of the things that our group talked about is that in a language like Python that has this truly maximalist syntax, right, where there are so many different pieces of syntax in Python, this notion of minimally working code is an excellent way to protect students from having to learn all of the little fiddly things about the language, right? They can do their physics just understanding how to make the computer calculate, and the skeleton of the minimally working code can do the other stuff with the very fiddly syntax. But the thing that our group observed is a teacher then needs to know all of those little fiddly bits, because if they're going to need to prepare their own minimally working code for the benefit of their students, then they need to understand these very nuanced things about the difference between a NumPy array and a Python list, and how file IO works. We encountered this in the extension to the Falling Through the Earth project. So one of the things that our group observed is that making minimally working code in a language with maximalist syntax like Python can be a large lift. And we talked about resources people can use to get support for that, like the pickup Slack.
Yeah, and I'll add on to that, Walter, you know, when you do this, you are also taking on the role of classroom tech support. And often that means being the person in the rooms who's willing to Google the error message, right? Because my students will get error messages that I've never seen before. And I say, well, let's go look this up. Oh, it's because this thing had to be an integer instead of a float. And I haven't told you about integers versus floats. And the question, I love getting this question from students. They'll always ask me, when was I supposed to learn this? And I just answer, now. You're supposed to learn it now when you need it. George, you've got a hand raised. Go ahead.
Yep. Probably, oddly enough, a number of years ago, I not only redid all of my undergraduate physics, but I also did the Python course out of EDX, which matches their first year or so of programming, which was all done in Python. It's probably one of the best classes I've taken in terms of learning Python is on the EDX platform. So I actually highly recommend it, because I still go back and reference the notes and book that I bought for that class. So it actually is a really good way to get at least familiar with the idea of dictionaries, lists, and gives you somewhat of a foundation to know all those ins and outs.
Yeah, definitely. Yeah, any experience you can get is definitely worthwhile. And it's kind of surprising how much you can do with just a little bit of experience. So part of what we're trying to do today is help you get more into the syntax, get more into working with a list or working with an array. There's also loads of tutorials out there. There's a lot of tutorials written from the Python programming perspective. So Geeks for Geeks is the site that keeps coming up in my search results. Their explanations are usually really good, and they give some good examples. I have a YouTube channel called Let's Code Physics that has a lot of Python tutorials in a physics context. So if you are looking for something that's a little bit more applied, a little bit more contextualized for you and your students, I try to keep those videos at about 10 minutes long, which is they tell us is the golden length for a video. Terry says in chat that real Python is wonderful as well. Well, cool. Sebastian, oh yeah, Philip, go ahead. We'll call on Philip, and then Sebastian will get ready to share.
Just real quick, is there a way, I was looking at some of the activities that were already on pickup, because absolutely, as a total beginner, having these scaffolded things are great for me. And I'm wondering if there's a collection of them already made that you can look at and go, okay, I would take on this activity with my students. But when I went to pick up it, I didn't see the place where you get the actual notebook.
Yeah, so it depends on the activity. Let me walk y'all through this, since it sounds like we're really interested in having stuff that is pre-made. And Walter, while I get one open, maybe you can share your answer. Go ahead.
I wanted to actually point out why that may be harder to find on the Pickup website. One of the, in my view, great strengths of Pickup is its language agnostic nature. That each pickup exercise is mostly a discussion, like what you read is mostly a discussion of the physics that you will teach and the numerical methods that you might use to do it, rather than specific programming implementation, because the idea is that every pickup exercise can be done in any language you like, because computational thinking in C and computational thinking in Python are the same kind of computational thinking. Mm-hmm. So we do have on the Pickup website sample codes for each exercise written in, usually it's the author's preferred language and then a couple of others. But those are kind of buried down further just because implementations in particular languages are not foremost in the way that Pickup thinks about pedagogy. So I hope that's cool.
Yeah, so here's an example from Kelly Roos, one of our fearless pickup leaders, on a falling sphere with air resistance, right? The thing we always have to ignore in high school physics. There's an entire activity about it. Like Walter was saying, when you go through these first three tabs, the instructor's guide, the theory, and the exercises, they are written language agnostic because we want you to be able to use these in any language. Now, there's a little bit of a joke that one of the P's in Pickup stands for Python, but that's not accurate. We have folks who work in lots of different languages. We just have a lot of vocal Pythonistas in the group. So you could, in principle, hand this to students and apply it to whatever language you are working in. So if you took Fortran back in the day and you're way more comfortable with Fortran than you are with Python, sure, you can have your students working in Fortran. But then you can come here and there are sample codes. This one's got sample codes in 9 different languages. They've got it in C, C++, Fortran, GlowScript, otherwise known as VPython, Haskell. Then there is a Jupyter notebook option. So like I can go down here, I can download this IPYNB file, that's IPython notebook, and I can then upload that to my Deep Note or upload it to my Google Colab space. And it's pretty much ready to go. Like you might need to tweak a little bit of wording or give the students a little bit of extra background depending on your context. But this is ready to go as another worksheet. So as the facilitator, you just need to review this, work through it yourself, maybe dig a little bit into how the functions work, etc. But other than that, it's already polished, ready to go. Walter is probably the foremost Python skeptic in Pickup. This is a fun conversation that you'll see if you come to a Pickup webinar. And what a lot of these will also have is solutions. So to help you with the grading aspect of it, you can compare the students' work against the solutions that are provided. The only thing you need in order to access these is an educator verified account on compadre.org, which is something you want to have anyway, because there's oodles of resources here on Compadre. The one thing I'll point out about the Pickup collection, you notice I brought up one that is listed as first year and beyond the first year. If you go to the search engine here, you'll see there are course levels. There is a high school designation, and there's only 5 that are designated for high school, but the high school designation was added only a couple of years ago. You notice that that all of these are written by Chris Orban, who works specifically in the high school teacher training context. And so he worked with the Pickup collection editors to add the high school designation. but that means there's stuff that came up before that designation that's probably high school appropriate, or can be made high school appropriate with just a little bit of adaptation. So when you go on here to search, I would encourage you to search both the high school and the first year tags, because that'll broaden it out to things that you can probably do in your class, at least with minimal adaptation. Let's see. Jeremy's asking, the Jupyter notebook files open to Deep Note and in Colab. Yes. So if you go over to Deep Note, what you'll see up here in the file name, if I can get it to show, let me see if I can get this to show. If you see over here, the notebooks you're working in are IPYNB files. So IPYNB is a Jupyter notebook file. That's what we are working in. Let's see. Mark says, my personal advice too is that if you like to learn from a book, to not pick an introduction to Python, rather get one from the physics perspective. And then he's got a recommendation there. He doesn't know that book specifically. Do not discount MATLAB. Yes, schools can get a district license for $500. They have full cloud support. Yes, MATLAB is I think a competitive favorite among the physics education crowd. Eugenia says, Mark, that book is really good. Okay, great. Matter Interactions Intro textbooks. It's also nice because it has Python integrated into the textbook. So Matter and Interactions, there's a debate on hashtag I Teach Physics about whether you can use that in a high school setting. Joe Hefner is convinced you can teach it and strip out the calculus. The authors are not quite so sure, but we would love to see somebody try and see how that goes. But yeah, I'm definitely on the Matter and Interactions bandwagon as well. Okay, Sebastian, if you're around, we would love to hear from you. Sebastian has worked through all of these modules himself over the span of a semester, so he had a little bit more breathing room, but Sebastian's actually taken this stuff and used it in his class, so we wanted to give him a few minutes to share with you about his experience.
Thank you, Brian. Good morning, everybody. As Brian said, I have had a few, I would say about 3 or 4 months of experience going through these modules, and once I started getting through them, I became really excited to use them in the classroom. And to kind of go back on what Brian was saying earlier about actually implementing this code and kind of learning based off of resources, like we said earlier, the internet is full of additional resources that you can use, and I found one of my favorite areas of resources is YouTube. And what I've also found is that the deeper I dug into the coding, the physics coding environment in YouTube or the community, the more my algorithm started giving me these YouTube recommendations, and I just started getting deeper and deeper into the algorithm. And so it's kind of helped me with that learning curve. And to just give kind of a brief description of what I saw whenever introducing this to my students was loads of excitement. A lot of the students tend to in the physics program, at least at my school, tend to want to use more technology. And I think that's part of our new digital era that we're moving into. And so when I was first introducing it, I was kind of just transitioning them into it, seeing how they kind of reacted to it with just describing what I was going to do, and they seemed very excited. So then the next stage of that was to try and implement it. Now, I did come across a couple of issues with actual implementation of it because of district restrictions on things like Google Colab. I also had a district restriction on Deep Note as well. And then now they've gone so far as restricting YouTube. And so there are a couple of hurdles that you can go through, or that you're going to come across depending on the district that you're in. And what I ended up doing to overcome that was, I'm in a Microsoft district, so I ended up using Visual Studio Code. Now, the implementation of it was a bit difficult because I had to have them download the IPYNB files, and then they opened it up on their Visual Studio Code. Or what I would do at first, before I actually found out about the Visual Studio Code, was I would just use Python on my computer, because I was able to open up Jupyter Notebook and just show them the graphs and functions and things like that. And so one of the things that I found was very beneficial for them was just the quick access to different coefficients, let's say, of of functions. Like for instance, when I started to teach I used it in my AP class as well. When I taught quantum mechanics and I tried describing the wave function, I was able to just quickly change what harmonic level I was at and show them how the energy is increasing and things like that with just the simple functions. And then later on with my IB class, I was using it as a review session. And like I had mentioned, putting in functions that can be quite simple to draw, but then the ease and the access to the actual functions themselves allowed the students to get a more hands-on experience with it. And so the amount of implementation wasn't as immense as I'd like, and I'm working towards getting more use out of the code in my classroom in the years to come. But I found it to be a very beneficial and very engaging environment for the students, and they tend to like the digital era. And so I'm excited in the future for the implementation of this code.
Thank you, Sebastian. Walter, go ahead.
So I'd like to offer condolences for anybody whose school systems have sold out to Microsoft. I do want to note that we're actually running our own. So Jupyter, just for reference, has a client server model, right? There's a Jupyter server somewhere in Google Colab or in DeepNote that's running these Jupyter notebooks. But if you can't use those because of IT tyranny, it's not that hard to set up your own Jupyter server. We're doing this here at Syracuse, and you can do it on any ordinary computer. So if that's something that you're interested in, I'm setting that up for our people. Ping me if you'd like to chat about what's involved in doing that, because it's really not that hard to run your own server.
Yes, we actually have 2 facilitators who can walk you through the process of setting up a local Jupyter server. We're going to hear about that, I think, on Friday when we talk about distribution implementation. Okay, thank you, Sebastian. Your insights directly in the field are definitely appreciated. Sebastian has kind of drunk double the Kool-Aid by going the quantum route as well, which is another set of workshops we'll offer at some point. We do, for those interested, we saw some interest on that in the chat. We do have, let me unpause my screen share here. We do have under afternoon choice time a set of quantum modules. Where do we, yeah, here under afternoon choice time, Spin's first introduction to quantum concepts. This is a great one to go through after you've got a little bit more experience with the Python, because this is a way you can introduce quantum concepts and step around all of the calculus that's usually involved in quantum by starting with a spin 1/2 system, and also teach your students a little bit of matrix algebra and a little bit of complex numbers. It's actually really cool. Okay, well, why don't we move on to our next topic for today, which is all about handling lab data in Python. So we'd love for you all to head to slide 18 in our slide deck. I put the link back in the chat. We'd love for everybody to take a sticky note. If you drag it off to the side and double click on one, you can tell us your answer to this question. Once you have lab data, what do you do with it and how?
Brian, I'm just going to go ahead and make a second copy of that slide, because if everyone participates, it's going to get pretty busy pretty quick. So duplicate it.
That sounds great. So you can pick slide 18 or slide 19 now. I think we built this slide deck when we had 20 people registered, so.
This is a good thing that we need more slides.
Although I just realized the text size is not auto adjusting, so I can go on and fix that once people are done typing.
Could you drop the Google link in chat again? I just switched computers and lost my chat history. I'm sorry.
There you go. Well, if there's something Zoom should have changed about their software by now, that chat history, I feel like should be top of the list.
There are many things Zoom should change about their software.
Yes.
At least it's not Teams.
Yes, thank you. Thank you. I still have yet to encounter anything Zoom will do that Discord won't.
I was using Discord for collecting pre-class reading assignments, and then discovered that if you accidentally delete a message in Discord, there's no getting it back. So that was my caution with Discord.
I don't think there's a whiteboard in Discord either.
Okay.
That's true.
No, but you could link to a Jamboard, and I love me some Jamboards.
When we were doing online teaching, I had to do an online class for 750, and we just turned it into a Twitch stream, and we had intro astronomy class on Twitch, and it worked great.
Students like their Twitch streams. Did you get any, oh shoot, what do they call it? Did you get any of that stream integration where they can put messages on the screen and everything?
We didn't do that, but I actually screen capped the chat and mirrored it back to the main feed.
All right, it looks like our activity has slowed down a little bit. So let's start reviewing these. If you're still typing or still thinking of something, feel free to add. Let's see. So I see in the upper right here, we've got make a claim. Yeah, what are the other two things you have to do in a lab report in addition to making a claim? We want evidence, and then we connect the claim to the evidence with
reasoning.
Reasoning, right? This is a big one in my classes. Is your evidence is the stuff nobody can disagree with. Your claim is the thing somebody might disagree with, and then your reasoning is how you keep them from disagreeing with you. So yeah, this is really cool because you know, again, now thinking ahead to the Jupyter notebook environment, how much easier is it going to be to do claim evidence reasoning with all of that stuff integrated? That's really cool. We use SparkView, so it collects data, plots data, and models the data all in the same place. Graph it and look for relationships, graph and analyze the graphs. Okay, seeing a lot of graphing here. That's good. It's like, that's kind of a thing we all agree on. Graphical analysis to determine the equation relating to variables, right? So when we say we're finding a relationship, usually we mean we're finding an equation that describes it, right? Students make a plot, usually to do a fit. Would love to hear a little bit more about what types of fits your students are doing. Let's see. Ooh, we got some folks advocating for Desmos. Yes, I need a good Desmos tutorial at some point. Let's see, usually graph it or linearize it. Yep, there's a popular option. Determine an unknown variable, linearization, curve fitting. Ooh, what's the difference between linearization and curve fitting? There's something to think about. Let's see. Kelly is obsessed with Desmos, but I use it more in my math classes than my physics classes. Yeah, I feel if somebody wanted to come to a pickup meeting and give a Desmos in physics workshop, I suspect it would be very highly attended because we don't, I mean, go look at the pickup collection. I don't think there's anything Desmos related on there, and there certainly could be. Let's take a look at slide 19. Graph by hand or use Vernier graphical analysis, apply a best fit function. Linearize, graph and analyze, put it into a text file, slurp it into a code running in your favorite language, do whatever you like it to. So Walter, I think I found yours. maybe not. Maybe I shouldn't guess things like that. Oh, Walter says linearization is transform your data such that if it does fit your model, the graph will be linear. A fit is so does my data actually fit my model? If so, what are the parameters, right? So the goal is the same. It's kind of a different mental process for the students. I don't think anybody's done a nice systematic study on the differences in the student mental processing space between linearization and curve fitting. I feel like that would be an interesting thing to explore. Not that I need more things on my list. There are people out there doing amazing physics things and distance turning into a physics engine. Awesome. Let's see. I guess that was mine. What was the tip off? Maybe the use of the word slurp, I think. Kurt Salisbury has a whole library of retro video game themed activities, and they're amazing. That's cool. Graphinator and Logger Pro. Yep, we're a Logger Pro department as well over here. Yes, Joe Emiliano did offer a summer class on Desmos last year. I did not have the time or the headspace to take it, but yes, I heard that was very well received. Another Twitter recommendation if you're looking for people to follow. Let's see, figure out how to linearize it. Okay, so I'm hearing a lot of graphing and a lot of data analysis, and a lot in spreadsheets or the native Logger Pro system, etc. So what we want to do today is help you learn how to do these exact same processes that you're already familiar with in a Jupyter notebook environment. So things like making a graph, getting some statistics. I don't think anybody mentioned average and standard deviation, things like that, but that's also valuable. Manipulating the data to linearize, fit with a model function, calculate new quantities, right? Because we don't measure energy, but we can calculate it based on the data that we have. Evaluate things that we know the answer to, G, E over M, things like that. And like y'all said, pretty much we're doing this in spreadsheets. Right. So maybe tell me either over microphone or over chat, what do you like about your spreadsheet systems and what frustrates you about them? Go ahead, Walter.
So one of my friends is a lab manager for a biophysics lab in our department, and she's not a programmer. So they do all their statistics in Excel. And one of her great complaints is Excel has like 6 different fit forms I can do. I can do a polynomial fit, I can do a log fit, I can do a linear fit. But if you get something that has some other mathematical form, you're sunk. You can't program in your own fit functions to Excel. And she complains about this all the time.
I mean, think about something as simple as, what if I have a power law fit plus a constant?
Yeah, it's stuff like that.
I mean, I can kludge that because I could subtract off a constant and fiddle with a constant until it works. But at that point, I'm doing the fit by hand anyway. Let's see. Summer says, the number of times I've had to tell students we don't measure energy, we collect other data to calculate energy. Yes, you can tell which students are thinking through the process by who says they measured energy in their lab report. I like that it's easy to fit a line, but I hate how difficult it is to make the graph in the first place. Oh yeah, especially when they changed some options in Google Sheets recently and I haven't recovered. Now they're using Google Sheets, collating class data makes it so handy. Yes, that is one thing that's nice, is if you can get a shared spreadsheet up, you can get students to do an experiment, each with a different parameter, and now you've got a, dare we say, big data set, if I can use that that jargon. Logger Pro has lots of built-in curve fits and the ability to make new ones, but the learning curve is steeper than Excel. Yeah, Logger Pro's custom function that is actually really useful if you can demystify it. When some data can be ignored and justifying it. Ooh, that's a good one. Students hate it when I tell them to throw out a data set. They think I'm committing physics blasphemy. Last time I looked, spreadsheets can't do log plot sensibly. Yeah, it's hard to catch exceptions and things like that. George, go ahead. Oh, George was not actually raising hand. Never mind.
There we go. Sorry.
Yeah, go ahead, George.
So we actually use Capstone, which actually allows all the error bars. You can do a custom function. You can do log, and that actually, and it has all of the basic statistics that actually works out fairly well, and it's relatively easy for the kids to pick up on, because when you're typing in for the custom function, it's sort of like typing in anything else. Our biggest issue is they don't read or remember what they've read 2 seconds after they've read it. But I actually like Capstone. It actually works out really well. The other one that works out really well, like I said, if you have it, the curve fit library in MATLAB is absolutely phenomenal. It allows you to literally you can type in whatever function you want. You'll get all of your statistics out of it. And you don't have to be able to program it. You can just say, here's my function, fit it. And that's one of the things that sometimes is annoying in Python is I've actually got to know how to do some programming to get the fit and get all the little bits and pieces out. So when I've used it, I tend to write the function myself and then tell them to just run this function.
Yeah, the other thing that's neat, we were talking yesterday about problems that don't have a closed form solution. So what if I'm trying to fit a model with air resistance?
Yeah.
Like I'm not going to be able to fit a function to that, but if I had my data and I had my computational model in the same place, I could work on getting those to overlap. And I feel like that's where it's really valuable for students, is to see that when we talk about modeling something, we're talking about making it match the data, right? So what we want to talk about today, and what we're going to send you off into your breakout rooms for in just a minute, is talk about how Python can do this stuff. If you're interested in working in this environment, if you're interested in kind of rolling out some computational activities, the lab is a great place to do this, because you can use Python to do with your lab analysis, to make your graphs, to make your curve fits, or to compare with a model. The thing we have to learn how to do, the part that's a little technical at the beginning, is learning how to read in the data and store it in the database. So that's the goal for today's activity. Let me give you a quick preview of what it looks like. We're going to go over to Clean Morning 2. Again, we switched everybody to a viewer role, so it should be much smoother this morning. And we checked and made sure it was clean yesterday. But basically what we're going to do is use, let me get down to the function. This is the function that takes care of reading in the data. It's going to read in an Excel file using the pandas library. So PD is pandas. I haven't figured out yet why a database library is called pandas. It's probably an acronym, or the developer's favorite animal or something like that. But once you have your spreadsheet up, either at a URL, or we'll be using Google Docs here, you can use it to read in, as long as you make that Google Sheet publicly accessible. So you just click share and make it so anyone on the internet with a link can view. You just put that link in here and it will read in that data into the Python environment. And then you're working with it just like you would the arrays that you were using yesterday. So this will be a little bit more familiar looking, I think, than yesterday, because it's the same type of activities you're accustomed to doing in a lab environment. We do have a sample data set for you to work with. So that URL I just showed you will take you to this spreadsheet. This is just some data I grabbed from one of our motion carts on a ramp. I think it goes up and then down. Yeah, it's got positive and then negative velocity. So this should look pretty familiar to you. A nice parabola in the position, a nice linear function in velocity, and a roughly constant acceleration. So if you have your own lab data that you'd like to work with, you're certainly welcome to do that. Or you can try out our sample data here and then switch over to your lab data later when you're a little bit more comfortable with the process. Oh, we got a little bit more in chat going on. Thank you, Walter, for finding that link for us, and thank you, Terry, for resharing the slides. So let's see, let's talk a little bit about breakout rooms here. So we'll have you work with the same partners as yesterday morning. So each morning you're going to work with the same group that you're familiar with. In the afternoons is when you get to choose based on your topic. So that's your opportunity to get to know other people. We'll ask you to take, we already did this, but we'll ask you to take about 10 minutes to recap what you learned yesterday. Just give each other friendly reminders. Oh, repasted Terry's. Haha, got it. Again, we'll ask you to engage in this process where one person shares their screen to do the driving. Oh, good question from Mark in the chat. Do people remember their room number from yesterday? If so, we can just have you pick your own room.